This video is a quick walkthrough on how we measure campsites in wilderness and other park and wildland management contexts so that we can track their number and their growth or their shrinking over time. So a campsite is a pretty important feature of a wilderness area, and it's a great way to kind of take the temperature on the health of how people are using that wilderness area for recreation. So we also, simultaneously to this, are doing things like paying attention to and monitoring wildlife populations, health, and ability to stay generally stable. We're monitoring things like the spread of any invasive species and our efforts to remove them or combat that. Monitoring things like wildland fire fuel loading and so forth. This is just another one of those things that we just track over time as a matter of course on pretty much every wilderness area. So let's talk a little bit about how to actually get the measurement done. So in your mind's eye, imagine that you're a part of a trail crew, and trail crews traditionally in land management agencies and organizations are the ones also doing campsite maintenance, and so they are going to be the ones heading out with sets of tools and provisions and so forth. And in the context of wilderness campsites, these trips to measure and repair campsites, or open up new sustainable ones, or close down badly destroyed ones that really need to go away. This is also sort of par for the course on these trips. So here's how we do it. Imagine a campsite in some part of the ecosystem wrapped by the wilderness boundary, and see the wilderness area, or excuse me, the campsite in the wilderness area in your mind's eye as nothing more than some kind of visual transition between the most natural surfaces present, like vegetation of various kinds and so forth, versus everything else. So we've got forest forbs, ground cover, and all of that outside of the campsite, and then you understand as a visitor or as a manager that this is a campsite pretty much for the fact that there are not any plants inside of that boundary. So there's going to be some kind of a typically sharp transition between bare soil and vegetated. In newly formed campsites, the transition is going to be from flattened vegetation, or impacted in some other way. It's maybe starting to get replaced by hardier invasive species, ones that tolerate or even thrive with disturbance, like getting camped upon, and upright or erect vegetation. But whatever the particular visible transition is, it tends to, again, form a very sort of sharply defined boundary, and that's what we're going to use as kind of the perimeter of our campsite. So how do we measure the size of this thing? Well, we could use a GPS and walk around the edge of this thing recording our track, and then back in the office, once we've done our work measuring a whole bunch of these out in the field, collecting data on all of them that we're able to, then we just create a polygon feature. And one of the very basic approaches or data points attached to every polygon feature in every geographic information system is what's the area of this polygon in whatever units you're using, typically square meters. Well, GPSs have battery issues, and a wilderness area doesn't have any electric plugs, so you're either schlepping very heavy batteries, typically lead acid batteries, and or solar panels to try and keep these devices charged up. Also, there's a coverage problem. A lot of wilderness areas are pretty exposed, meaning they're not under heavy canopy. And then again, a lot of wilderness areas are under very dense canopy, which makes it very difficult for a GPS to accurately capture what's going on when you're trying to record something. Instead of precisely moving along the edge of the campsite in its recordings, it's collecting a point typically every second, or several points a second if it's a very, very high-powered GPS. And when we've got a whole bunch of canopy cover, or as is often the case in more mountainous or rugged wilderness areas, we've got a whole bunch of mountains and ridge lines that are blocking the GPS signal from the satellites that are low on the horizon. And so GPS is a great tool. It's very effective, very efficient when it works. It's not always the right tool for places like wilderness areas because, gosh, there's just a lot extra stuff to manage. And in wilderness management, we have to use the minimum tool available, and GPS is sometimes not that. So what's another way to measure campsite area? We could use something like a geometric approximation method and say, okay, so this campsite isn't exactly circular or elliptical, but we could probably, in our mind's eye, find sort of the center, or what's called the centroid of the site, and kind of mentally draw a circle that basically captures the area of that. And then if we just record the radius, then we'll have something pretty close to the area of the site. That's okay, but it's pretty approximate. This is going to be a rough guesstimate. Now, working in our favor, we have the idea that a lot of campsites are generally fairly geometrically shaped. Typically not a pure circle, but something like an ellipse is pretty easy to get. So we want, if it is elliptical, we're going to get not one but two radii. We're going to measure what's called the semi-minor axis and the semi-major axis, and then use those to get some area. That's pretty accurate. And in some management cases where we just need a go, no go, is this a good, sustainable site, or is it growing over time? This is a very quick indicator of gross changes or major, easily observable changes over time. So we're not measuring this every year, but a couple of times a decade, 3-4 times a decade, we're measuring all of these campsites and seeing if they're growing and growing and growing. That's bad. This area is impacted. So outside of that radius, we're going to have less impact. And as the manager, if you're trying to keep this place sustainable or preserved, if this is a Park Service wilderness area, then preservation is a standard that we have to build to. And impact is going to be something that we are required to deal with. So let's figure out a third way that might give us a little bit more precision, a little bit more sense of what the actual changes present are. This is going to be what's called the variable radial transect method. And this is also going to use a geometric approach, but it's going to be a little bit more sophisticated. Now, we don't have to worry about any of the math that we're about to get into in the field. We're just taking measurements, and we can throw all this into an Excel spreadsheet or a form that we keep and maintain and just add to over the years back in the office when we don't have to think about any math, which is really nice. We can let the spreadsheet and the software do all that calculation and thinking and heavy lifting for us. The basic idea here is we're going to pick any point on the campsite and then stand in that point and measure two things about a bunch of different variable length radii. So each one of these measurements that you take is going to be a different length, and you get to choose how many of these you need in order to get a pretty good sense of what this site is shaped like as well as its size. So for each one of these radii, we're just measuring two things, and I'll label each one so we can kind of track it as we go. This first one is going to be radius A, B, C, D, and so on. In this case, clockwise, although it doesn't particularly matter which way you go, as long as you're recording them in order. H, radius I, radius J. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 radii. We could get approximately the same information from 8 radii, and approximately the same information but slightly more accurate from 16 radii. We could get a really, really precise measurement from 100 radii, but that would take a long time and be a bunch of extra data entry. So, again, because this is the variable radial transect method, you get to choose how many radii will approximately capture what's going on with this particular campsite. So, this method is pretty functional with campsites that are very circular. This method is very functional with campsites that have sort of sharply defined corners, as is sometimes the case. And this is also really good for the most common case where we have sort of strangely shaped campsites, more amoeba-like or amorphous in their shape. And this is often the case when we have, as in most forested campsites, where we have trees around the edge, and those trees tend to prevent further expansion of the campsite in that particular spot, and allow, or even promote in some cases, expansion around each one of those tree trunks or root wads. So, in this case, in all of these cases, the variable radial transect is going to get you the information that you need. And in the case of sharp corners and sharp turns on the perimeter of the campsite, aim your radii at those corners or sharp turns, because you don't get any extra information or accuracy by hitting the middle of a straight segment along the edge. If you're not sure why that is, take a moment to think for yourself on what we are building towards. You'll notice that each pair of adjacent radii forms a triangle. And a triangle is going to be what we need to very quickly, easily, and accurately get the area of that part of the campsite. And we'll just add all those up, again in a spreadsheet. We're not having to do any math out in the field. And that's the total area of our campsite. So triangle 1 plus 2 plus 3 plus 4 in the case of this sharply angled campsite, that's going to be the total area just by combining all of those. So let's go back to our original example and figure out what we got to record. So for each of these various radii, again, we've got 10 of them in this case. It could be 8, could be 12, could be 15, could be 5. Doesn't matter how many radii, just whatever number gets you the best approximation of that particular shape. The way that we proceed from here is for each radius, we record the length and the direction, which of course in forestry we call the azimuth or the compass reading. And so we would always be consistent with our units. Azimuth is always going to be in degrees, and our length is always going to be in, let's say, meters. We're not going to use the imperial system because we're not animals. Okay, let's recreate this so we got a little bit more space. Here's our campsite. Here's an arbitrary center point. As long as you use the same center point, doesn't matter where it is. Here's our first radius, our second radius, third, fourth, fifth, sixth. Now, what we're actually going to record is not precisely the area of this site. We're just going to get a really good estimation. This is a management technique, not a science technique. So it doesn't need to be perfectly accurate in terms of area down to the atoms bounded by this edge. So here's what happens when we set up and record the information we need to calculate the area of each of these triangles. See how these triangles are largely going to underestimate the area of the campsite a little bit? The way that we kind of fix that error is with more radii. So out in the field, again, you're making decisions on, okay, well, 6 radii is going to give me a pretty big underestimate of the area. So all of this space here, and here, and here, etc., that's all going to get missed by tallying up the sizes of these triangles. So by adding more radii, we lower that error, but we spend more time in the field doing it. So again, you as a professional get to choose how much effort to sink into this in order to approach a functional level of accuracy. So we divide that triangle down into smaller ones, and the missed area around the edge of that perimeter much, much smaller. Good to go. All right, I'll label these radii again. A, B, C, D, E, F, G, H. And then let's just record what we see about it. So length in meters and azimuth in degrees. For A, our length, let's say that's about 3.1 meters. And the azimuth is just past east, if north is up on our screen. So the azimuth is just going to be a little bit past 90. Let's call that 105 degrees. And B is almost pointing south, but not quite, so let's call that 4.1 meters. And at 175 degrees. And C is a little bit longer again, so let's call that 4.9 meters. And that's going to be, well, it looks like it's about parallel to kind of the southwesterly direction. So that's going to be 180 plus 45. Let's call that 225 degrees along that radius. Okay? And so on around the table. D is going to be 5.1 meters at about 270 degrees, or let's call that due west. E is going to be, let's see, 4.2 meters, approximately going northwest in this case, so that'll be 270 plus 45, or 315 degrees. Radius F is just shy of north, so let's call that 340 degrees north by northwest, and about 4.2 meters once again. Radius G, let's call that 15 degrees off of north, so north by northeast, and 3.0 meters. And our last radius H, 2.6 meters, and at about 40 degrees, just shy of northeast to the northerly side. Okay, so now we've got a whole bunch of lengths and a whole bunch of directions for these rays, these radii that are pointing out from our arbitrarily chosen point. That's all we need to do on that campsite for this particular kind of data. So our next move back in the office is to pull up our list of radii paired with their directions and lengths and recreate what's meant by those measurements, just those triangles. So got it kind of like this, and so forth on around. Now, the next move is to figure out the area of each of these triangles, and we know enough now to be able to do that. One way that we can calculate the area of a triangle is by knowing two adjacent sides' length and then the angle between them. So that's going to be, here is side number 1, here's the angle formed between those two sides, and here's side number 2. Okay. Now, in this case, side number 1 is the same thing as radius A. And we know that radius A is 3.1 meters long, and radius B is 4.1 meters long. Hopefully, we can easily calculate the angle between these two rays without having to measure that angle and record another third thing in the field. Because we know what direction each of those rays are facing, we can subtract the smaller from the larger and get exactly where we need to go. Unless that wraps across 360, in which case we need to handle the math just a little bit differently. But it's still not that hard. So 175 degrees for radius B minus 105 degrees for radius A corresponds to a 70-degree angle between radius A, labeled side 1, and radius B, labeled side 2. Okay? Cool. Now, it gets down to trigonometry. And with trigonometry, we can get into the area very simply, using the side angle side formula. Okay? So I'll write that down for you. And in practice, remember, we've got, let's say, on average, a dozen radii for each campsite. And let's say for a big wilderness area, we've got 250 campsites. Okay, so that's a couple of thousand measurements that we've taken and recorded. We're never going to be doing this by hand with a calculator because we're going to get typographic errors and all kinds of problems. We're always going to dump this into a spreadsheet, program in the side angle side area formula, and let the spreadsheet never make a mistake from that point forward. Okay, so side angle side area of a triangle is, let's see here, two sides and the included angle given. Okay, so we've written it out in kind of long form here for you, so for those of you who absolutely hate math, we can just kind of talk our way through it. The area of a triangle is equal to the overall quantity of the length of side A times the length of side B times the sine of the angle formed by those two sides A and B. Whatever that angle is, in our example, again, it's 70 degrees. Take the sine of that angle, multiply those three things together, and then divide that whole shebang by 2, because remember, with all areas of triangles, this is basically just figuring out the area of the rectangle involved, and then forgetting the other half of the rectangle that the triangle doesn't occupy. So, written in a more compact and concise format for those of us who are math heads, area equals A times B times sine of angle AB all over the quantity 2. Pretty simple. It's just multiplication and division, and then we got that one trigonometry term in there, but that's what calculators are for. We don't need to look up any trig tables, and again, we never have to worry about this stuff in the field. So, in our example, that'll be 3.1 meters times 4.1 meters times sine of 70 degrees all over 2. And that simplifies down to 12.71 times the sine of 70 divided by 2. Which is the same as 6.355 times sine of 70 which is the same as 6.355 times excuse me, 0.7738906.816, which simplifies down to 4.918 meters square. Now remember, this is not the area of our campsite. This is just the area of that particular triangle in our campsite. So now we know what the area of our one triangle is, and it's the exact same operation for every other pair of adjacent triangles. Okay, so let's label that 4.918 meters squared. And then repeating that operation across the whole thing gives you the area of the whole thing. Okay? So, I'll type this up, this example for us, and throw that into a spreadsheet. And we'll use this as a class to practice on this example campsite. What is the area of this imaginary place? And then you can imagine going back to it 3 years later and seeing if it's any bigger or any smaller. We will typically get campsites formed when people start using a new place in less than one season. Just takes a couple of tent nights on vegetation to start killing everything off and so forth. And it can take up to a decade or more, in some cases many more years than that, for a campsite to rehabilitate itself naturally to undetectable levels of human impact. So that kind of underscores the urgency and the importance of doing this monitoring work. We got to keep a finger on the pulse of, are our campsites growing in number? Are they growing in size? Are they growing in impact within that size? Very tricky stuff. Okay, so head to our course website and look for the link in this assignment to the spreadsheet that reproduces this example. Work through that example, and we'll be able to add to it throughout the semester as we go. Good luck. If you have any questions, let me know.